Uh, so let me start from here. So what I want to do today is really to derive an equation and to show you how to derive an equation to govern the fin thickness. So suppose I deposit some fluid on a solid substrate. It's solid, and there's some fluid here, and this one is a free surface. So it's some thickness h, x, and t. And the question is how to derive an evolution equation for this fin thickness. So typically for Newtonian fluid, you need to describe the whole system by the velocity field and the pressure, and also with some boundary condition at the free interface. And for nematic liquid crystal, not only that, you also need to have the directed field.
Again, you are talking about one-dimensional.
One dimension, yeah. So, this is the content of my talk. In the very beginning, I will show some introduction, some motivation from the experiment, and show you how to derive this kind of thin-film equation for Newtonian flow. And then I'll go to nematic liquid crystal. And firstly, for the strong anchoring model, how we derive the equation, and secondly, for the weak anchoring model, how we do that, and discuss some of the stability of the fin. So the first motivation experiment we have is this one, that you had they deposit some nematic liquid crystal on a solid substrate with some specific thickness. And this is very thin film you can see here. For A, it's 0.44 micron, and this one is 0.32 micron and 0.16 micron. And you see the stripe pattern, there's stripe pattern of the directed field. So you see the instability for different fin thickness. And the question is why you have this kind of instability for a fin. And the second is when you deposit a nematic liquid crystal droplet on a solid substrate and just let it spread. And you will see this kind of fingering at the contact line. And this is really different from the Newtonian flow. When you have a Newtonian droplet, you just put it on a table and let it spread. It's stable because of a surface tension. So the contact line is always circular and just bending outward. However, for nematic liquid crystal, you see this is a snapshot of a contact line at the increasing time. You see this kind of fingering behavior. And the question is why you have this kind of system, why you see that, and why it's the case. Yeah. So typically, to derive the evolution equation for a spin thickness, there are two different approaches. One is from hydrodynamic, the other one is from thermodynamic. So for hydrodynamic, if you take the Navier-Stokes equation and imposing the long wave scaling, and the most important thing is this delta is the ratio between the fin thickness and the spatial length scale. So this phi is the scale for fin thickness with this L, the spatial length scale. And this one is very small, so that means the fin is very, very thin. And when you have this delta, which is a small parameter, you can expand the Navier-Stokes equation. And at leading order, you can actually solve for its pressure and the velocity field. So the pressure will be a function of the fin thickness, and its velocity can be returned as a function of fin thickness as well. And then you can plug into the conservation of mass for a fin, and you end up with this thin film equation. The gamma is the surface tension. So this is a hydrodynamic approach to derive this fin thickness evolution equation. And on the other hand, you can use thermodynamic to do the same thing. You write down the long wave free energy functional of a nematic, of a Newtonian fin, and it turns out to be the gamma, which is the surface tension. So energy functional is really the integration of this gamma across the free surface. So ds is the surface element, and in a long wave approximation, the ds can be returned as this one. And the evolution of the field need to follow the gradient of this kind of energy. So it always goes to minimize the energy. And this formulation turns out to be the simplest form for a conserved field. So you just plug in this free energy functional into this kind of formulation, then you got the evolution equation for fin thickness. And I want to point out that this one, equation 2, that comes from thermodynamics, is exactly the same with the one you have from hydrodynamics. 1 and 2 is almost exactly the same when you choose this Q, the mobility function, to be this one. So you have two approaches to derive the evolution of the fin thickness. And now I want to go to nematic liquid crystal. So for nematic liquid crystal in 2D, you not only need to have the pressure and velocity, you also need to have the direct field, which is this one, sine theta and cosine theta. And then also I want to point out that for nematic liquid crystal, typically what I found is the direct field like to align planar in the solid and liquid interface, and like to align vertical for the liquid and air interface. So it's an LC here. So apparently there's a kind of elasticity. You need to bend the director field, the director from horizontal to vertical. So you need to take this one into account. And this is done by consider the Fang-Hua elastic energy, which is this one. So the total free energy functional of a nematic film can be written as the following. It's an integration of this elastic energy across the film and plus the interfacial surface energy. This is a strong anchoring model, so I always assume that it's vertical in this free surface and it's always horizontal here. So there's no other surface energy. And once you have that, and because, here this functional is a functional of two independent fields, H and theta, and it's quite complicated. So we want to simplify. We assume that this elastic constant K is in this order. Then we can reduce the problem to say that the direct field reacts fast and always maintains steady state. So the direct field is react really fast compared to the fluid flow. So when the fluid flows, the direct field is always in a steady state and turns out to be a linear function in a z direction. And then you can reduce the free energy functional to be a function of fin thickness only. Then just plug into the thermodynamic gradient dynamic of formulation, then you have the evolution for fin thickness. So compared to the previous Newtonian model, Newtonian thin film equation, this one is come from surface tension, is the same with the Newtonian one, and this one is the Newton that come from bulk elasticity of the nematic liquid crystal. So here I want to show you again how we derive the same equation from hydrodynamics. Again, you use the Erickson-Leslie formulation and impose the long wave scaling. You can reduce the full Erickson-Leslie formulation to these three equations, and also the continuity equation, I forgot to put it here, with some boundary condition. Then you can solve for the pressure and solve for the velocity, and then use the conservation of mass. You end up with this evolution equation, where the Q can be fully determined by doing an integration along the nematic elasticity. The Q is a function of HQ. It's proportional to HQ. And also, this one, the evolution equation, this one is exactly the same with the one that we derived from thermodynamic principle. So in a brief summary, for strong anchoring model, we have this equation for the fin thickness, where this term comes from surface tension, this term comes from the nematic elasticity. You can see that K2 is a constant and Q9 is a constant. So nematic elasticity only gives you this one. Second derivative of the fin thickness turns out to be a diffusion. So the strong anchoring is always stable because it's just a diffusion. Here we show the simple linear stability analysis by perturbing the stress fin for small perturbation and try to find the growth rate. And growth rate is always negative for any wave number, so it's always stabilizing. So nematic elasticity is always stabilizing in the case of a strong anchoring. So now we want to go to a weak anchoring model. So for a weak anchoring model, the surface not only have this gamma as a constant, but also have this weak anchoring energy. It's in the Raffini parabola form. So I denote this psi to be a difference between the director at the solid substrate and at the free surface. So psi is the difference between these two. So here we assume again a fast directed relaxation. So the free energy function of the variation of the free energy with respect to the angle theta equal to 0, then you end up with this theta to be linear in the z direction. However, the difference is that this psi is a function of something. It's a function of the fin thickness. It's not a constant anymore. For a strong anchoring model, this psi is always a constant. So it always goes from planar to homeotropic at the free surface. But here it's not the case. So let's assume for a moment that this psi is some function of h, that you know how to solve it. Then we can reduce this free energy functional to be totally a function of fin thickness only. Then once again, you can use the gradient dynamic formulation, just plug in this form, then you obtain the evolution of the fin thickness. So right now we have a Newton here. This one again comes from the nematic elasticity. And the strong anchoring model is recovered when this psi is replaced by a constant. Then you can fully recover the strong anchoring model. And right now, this is a weak anchoring model, so this psi is not constant, but a function of the fin thickness. So here I show you how to solve for psi. So you take the variation of the free energy functional, you end up with this equation. It turns out that psi needs to satisfy this equation. Unfortunately, there's a line here that is almost invisible. So you can see that psi equal to 0 is always a solution. That means a homogeneous state. Remember, psi is the difference between the angle at the solid substrate and at the free surface. So psi equal to 0, there's no.
Would you remind, please, A capital? What is it? A capital?
Oh yeah, the K is the strength of the.
A capital.
A is the strength of the surface anchoring energy. Yeah, so you have this critical fin thickness. So the homogeneous state is always a solution, but when you pass the critical fin thickness, there are two other solutions appear, which turns out to be a distorted state. And when you write down energy, you found that the distorted state have a lower energy, which is energetically more favorable. So this is how you solve the psi. You just take one over branch and plug into the equation that we had before, then you have an evolution of the fin thickness. However, as we know that this is a pitchfork bifurcation, which is quite unstable. If we impose any small perturbation, this pitchfork will break into a steady state and a saddle-node bifurcation. So we just introduce a small perturbation to this surface anchoring energy, which leads us to automatic selection of one over the branch with a psi. Yeah, so then you can plug in this psi into the weak anchoring model, and you know what's the evolution of the fin thickness. Here I show you the linear stability of a flat fin. So you do the same thing as before, and you found that actually there is a range of thickness that is linearly unstable. It's between the critical thickness and the critical thickness multiplied by a constant, pi over 2. So let me show you here a numerical simulation. So in the very beginning, I have a flat fin but with a small perturbation here, and it's in the linearly unstable range. So it's linearly unstable, so it's going to grow and into some droplets. And well, in this figure, I show you the energy. So the red line is the surface tension energy, energy corresponding to surface tension. The green one is the bulk elasticity, and the purple one is the surface anchoring energy, and the total energy is the black one. And you can see that when time goes, the total energy is really decreased. So this one is really the one with the lower energy compared to the flat fin. So also here I show you how to derive the evolution equation in three-dimensional when consider the directed field. The directed field is this form. Yeah, so you can derive this equation from hydrodynamic approach using long wave approximation, and you end up with this equation. I think I run out of time, so let me show this page first. So here's my collaborator, Wojtile and Andy Archer in Loughborough, and Linda Cummins and Lukandish in New Jersey Institute of Technology. And let me just leave this conclusion page, and thank you for your attention.
I think we still have a couple of minutes for quick questions.
For some fields, I would expect van der Waals forces are important when you are neglected.
Yeah, but we can include it. Yeah, but here in this project, we just want to analyze the influence of the nematic elasticity. But yeah, for sure we can include it here, and for sure it's important when you have a very very thin field. Yeah.
Any further question? Well, I have one. Apparently, your critical thickness is nothing but the extrapolation length of the anchoring.
Yeah, that's right.
So it means that when the thickness is larger than the extrapolation length, it becomes unstable.
Yeah.
Is this bottom line? Or?
Yeah, right, correct. But much more than that, when you go to thicker fin, it's stable because of its triangle. So there's a range between them to be an unstable field.
Well, thank you very much for your presentation.